Relative atomic mass is a dimensionless physical quantity. The ratio of the average mass of atoms of an element to 1/12 of the mass of an atom of carbon-12. The relative atomic mass is a statistical term, referring to an abundance-weighted figure involving measurement of many atoms. As in all related terms, the word "a relative" refers to making the figure relative to carbon-12, so that the final figure is dimensionless. The term relative atomic mass is exactly equivalent to atomic weight, which is the older term. In technical usage, these values are sample-specific when a natural element source is composed of more than one isotope. Thus, two samples of a chemical element, which is naturally found as being composed of more than one isotope, collected from two substantially different sources, are expected to give slightly different relative atomic masses. Because isotopic concentrations typically vary slightly due to the history of the source, these values differences are real and repeatable, and can be used to identify specific samples. For example, a sample of elemental carbon from volcanic methane will have a different relative atomic mass than one collected from plant or animal tissues. In short, the atomic weight of carbon varies slightly from place to place and from source to source, a fact that can be useful. However, a typical figure also can be useful, as follows. Both the terms relative atomic mass and atomic weight are sometimes loosely used to refer to a technically different standardized expectation value, called the standard atomic weight. This value is the mean value of atomic weights of a number of normal samples of the element in question. For this definition, a normal sample is any reasonably possible source of the element or its compounds in commerce for industry and science and has not been subject to significant modification of isotopic composition within a geologically brief period. These standard atomic weights are published at regular intervals by the Commission on Isotopic Abundances and Atomic Weights of the International Union of Pure and Applied Chemistry. The standard values are intended as mean values that compensate for small variances in the isotopic composition of the chemical elements across a range of ordinary samples on Earth, and thus to be applicable to normal laboratory materials. However, they may not accurately reflect values from samples from unusual locations or extraterrestrial objects, which often have more widely variant isotopic compositions. The standard atomic weights are reprinted in a wide variety of textbooks, commercial catalogs, periodic table wall charts, etc. And in the table below, they are what chemists loosely call atomic weights. The continued use of the term atomic weight, as opposed to relative atomic mass, has attracted considerable controversy since at least the 1960s. Mainly due to the technical difference between weight and mass in physics. Both terms are officially sanctioned by IUPAC. The term relative atomic mass now seems to be gaining as the preferred term over atomic weight, although in the case of standard atomic weight, this shorter term continues to be preferred. Definition: relative atomic mass is a synonym for atomic weight, and in some circumstances may even be synonymous with standard atomic weight. It is an average atomic mass, or the weighted mean of the atomic masses of all the atoms of a particular chemical element found in a particular sample, which is then standardized by comparison to carbon-12. Relative atomic mass is frequently used as a synonym for the standard atomic weight, and it is correct to do so if the relative atomic mass used is that for an element from Earth under defined conditions. However, relative atomic mass covers more than standard atomic weights, and is a less specific term that may more broadly refer to non-terrestrial environments and highly specific terrestrial environments that deviate from Earth average or have different certainties than do the standard atomic weights. Standard atomic weight refers to the expected relative atomic mass or atomic weight of an element sample in the local environment of the Earth's crust and atmosphere as determined by the IUPAC Commission on Atomic Weights and Isotopic Abundances. Because these standard atomic weights are an average of relative isotopic masses for a given element from different sources, standard atomic weights are subject to natural variation. An uncertainty in brackets or an expectation interval may therefore be included in sources of standard atomic weights. This uncertainty reflects natural variability in isotopic distribution for an element, rather than uncertainty in measurement. Although there is an attempt to cover the range of variability on Earth with standard atomic weight figures, there are known cases of mineral samples which contain elements with atomic weights that are outliers from the standard atomic weight range. Lithium represents a unique case where the natural abundances of the isotopes have in some cases been found to have been perturbed by human isotopic separation activities to the point of affecting the uncertainty in its standard atomic weight, even in samples obtained from natural sources, such as rivers. For synthetic elements, the isotope formed depends on the means of synthesis, so the concept of natural isotope abundance has no meaning. Therefore, for synthetic elements, the total nucleon count of the most stable isotope is listed in brackets, in place of the standard atomic weight. When the term atomic weight is used in chemistry, usually it is the more specific standard atomic weight that is implied. It is standard atomic weights that are used in periodic tables and many standard references in ordinary terrestrial chemistry. Current definition prevailing IUPAC definitions taken from the Gold Book are atomic weight, c. relative atomic mass and relative atomic mass, the ratio of the average mass of the atom to the unified atomic mass unit. Here the unified atomic mass unit refers to 1/12 of the mass of an atom of 12C in its ground state. The IUPAC definition of relative atomic mass is: an atomic weight of an element from a specified source is the ratio of the average mass per atom of the element to 1/12 of the mass of an atom of 12C. The definition deliberately specifies an atomic weight, as an element will have different relative atomic masses depending on the source. For example, boron from Turkey has a lower relative atomic mass than boron from California, because of its different isotopic composition. Nevertheless, given the cost and difficulty of isotope analysis, it is usual to use the tabulated values of standard atomic weights which are ubiquitous in chemical laboratories. Historical older historical relative scales used either the oxygen-16 relative isotopic mass for reference, or else the oxygen relative atomic mass for reference. See the article on the history of the modern unified atomic mass unit for the resolution of these problems in 1961. Differing terms referring to the mass of single atoms. Relative isotopic mass is a similar sounding term which refers to a quite different quantity, specifically the ratio of the mass of a single atom to the mass of a unified atomic mass unit, expressed as a dimensionless number. The relative isotopic mass is discussed in the article on atomic mass, with which it is synonymous, save for choice of mass units. Naming controversy. The use of the name atomic weight has attracted a great deal of controversy among scientists. Objectors to the name usually prefer the term relative atomic mass. The basic objection is that atomic weight is not a weight, that is the force exerted on an object in a gravitational field, measured in units of force such as the Newton or poundal. In reply, supporters of the term atomic weight point out that the name has been in continuous use for the same quantity since it was first conceptualized in 1808. For most of that time, atomic weights really were measured by weighing, and that the name of a physical quantity should not change simply because the method of its determination has changed. The term relative atomic mass should be reserved for the mass of a specific nuclide, while atomic weight be used for the weighted mean of the atomic masses over all the atoms in the sample. It is not uncommon to have misleading names of physical quantities which are retained for historical reasons, such as electromotive force, which is not a force, resolving power, which is not a power quantity, molar concentration, which is not a molar quantity. It could be added that atomic weight is often not truly atomic, either, as it does not correspond to the property of any individual atom. The same argument could be made against relative atomic mass, used in this sense. Determination of relative atomic mass. Modern relative atomic masses are calculated from measured values of atomic mass and isotopic composition of a sample. Highly accurate atomic masses are available for virtually all non-radioactive nuclides, but isotopic compositions are both harder to measure to high precision and more subject to variation between samples. For this reason, the relative atomic masses of the 22 mononuclidic elements are known to especially high accuracy. For example, there is an uncertainty of only 1 part in 38 million for the relative atomic mass of fluorine, a precision which is greater than the current best value for the Avogadro constant. The calculation is exemplified for silicon, whose relative atomic mass is especially important in metrology. Silicon exists in nature as a mixture of 3 isotopes, 28C, 29C and 30C. The atomic masses of these nuclides are known to a precision of 1 part in 14 billion for 28C and about 1 part in 1 billion for the others. However, the range of natural abundance for the isotopes is such that the standard abundance can only be given to about plus or minus 0.001%. The calculation is R equals plus equals 28.0854. The estimation of the uncertainty is complicated, especially as the sample distribution is not necessarily symmetrical. The IUPAC standard relative atomic masses are quoted with estimated symmetrical uncertainties, and the value for silicon is 28.0855. The relative standard uncertainty in this value is 1 times 10 to 5 or 10 ppm. To further reflect this natural variability, in 2010, IUPAC made the decision to list the relative atomic masses of 10 elements as an interval rather than a fixed number. Periodic table with relative atomic masses.